What I'm going to talk to you about today, uh, as Gunnar asked me, is photonic integrated circuits. But I'm going to dive a little bit more deeper into silicon photonics and silicon nitride photonics, and then finally into programmable photonics. So, just a few words about myself. So, as already introduced, I'm part of the Photonics Research Group in Ghent. So that's a fairly large research group of about almost 100 people, 9 professors. We do make photonic systems on a chip for a variety of applications. So telecommunication, datacom, biomedical applications, sensing, etc. Our key technology is silicon photonics, where we make use of IMEX silicon photonics platforms, but we also look into different material systems, especially where silicon is lacking some functionality. So in this presentation, I'm gonna start very basic on photonic integrated circuits, then move towards larger scale circuits and silicon photonics, and then finally end with the topics that I'm working on myself mostly today is programmable photonics. So the basic rationale is manipulation of light. I mean, if you look at light is extremely useful. It contains a lot of information. So you can carry information in the power, the phase, the beam profiles, the polarization, the wavelength of the light. And that's why we want to process light, because we can use it for sensing, we can use it to transport information. Now, if you look in more detail into what light is, we guess all know that light is an electromagnetic wave with a time oscillation and a spatial oscillation that propagates, and that you also have an electrical and magnetic field in there. At the same time, you can represent light as a flux of photons. So where each photon carries an energy that is proportional to the frequency. Now, light finds its use in a lot of different applications. The largest application of lights or of lasers, for instance, today is in material processing. Laser cutting, laser welding, laser scribing, etc. But then displays, telecommunication, sensing are also very, very important applications of light. And then recently, there's been more and more talk about using light for computing. It was actually the cover of Nature this week was about an optical brain-inspired computer. Now, the key driver today for photonics, and if we talk about photonics, we're usually talking about manipulating light on a small scale, is communication. Essentially, the entire internet traffic runs over optical fibers, and without those each of these optical fibers needs to have a transceiver at the beginning and the end. Now, optical communication, unlike what most people think, optical communication is not new. Optical communication has been around for ages, even since the early days of mankind. And the first version of the internet was actually an optical communication network installed in France in the 18th century, which was called the semaphores. And it was an optical network. You could send messages from the south of France to Paris in a matter of hours, which was much more efficient than any other communication method. Now, okay, optical communication got displaced by electrical communication only actually for a fairly short time. The introduction of telegraph, introduction of the wireless was the transition from optical to electrical communication. But that quickly changed from the 1960s on with the introduction of a laser. And since the introduction of the laser and the introduction of the optical fiber, optical communication has again dominated the amount of data traffic. Now, just to understand what is needed to make an optical link, you need a light source, which can, for instance, be a laser, because that gives you the highest quality of light. Then you need to encode a signal onto that light source, and that can be done by either switching the laser itself on and off, or by using an extra modulator, which, for instance, modulates the amplitude or the phase or the polarization of the light. And then you have to transmit that signal over a medium, and at the end, your output signal comes out at the detector on the right side. Now, optical links can scale quite well. They can scale to hundreds of gigabits per second on just a simple schematic like this. Now, there's a problem with light, if you want to use it for communication, is that light has the tendency to travel in a straight line. So if you want to route light to whatever place you want, you need some mechanism. You need a kind of waveguide that helps you guide light to the point where you want it. So optical waveguides are essential in photonics. Now, if you have your diffraction of light, which you can describe as light rays, you need some way to confine them. And the way to do that in optics is with a dielectric waveguide. In microwave signals, you can use metallic waveguides, but in optics, metals have too much loss, so you need some form of dielectric confinement with materials that do not absorb the light. And the trick is actually very simple. You take a material with a high refractive index and you surround it with a material of lower refractive index. And then the light, the beams of light or the rays of light are confined in the high index material. Now, this is not a human invention. Nature was there first. Nature always is there first. So you find the first or some natural form of optical fibers, you find it in certain rocks and minerals. But the breakthrough was with optical fibers was to be able to make glasses that really had extremely low optical losses. And that enabled the use of waveguides throughout the world and essentially powering the internet. Now, why are optical fibers so useful for optical communication? Well, first of all, they have been engineered to have extremely low loss, but they always also have almost unlimited bandwidth. If you look at electrical signals, we're talking about signals that are on the order of 10 gigahertz radio signals, and maybe we can push that up to 60 gigahertz radio signals. But if you look to the optical domain, optical waves are also electromagnetic waves. They're similar to radio waves, but now you have frequencies of the order of 200 terahertz, and you have a useful bandwidth of 40 terahertz. That is an enormous amount compared to what you have for simple radio communication. Now, it's not that easy to use that 40 terahertz that you see here in one go. That's quite a challenge. So what people usually do is chop it up into wavelength channels. And frequency and wavelength are a kind of interchangeable quantity. So you can chop up these 40 terahertz into a lot of different channels, with each a bandwidth that can be modulated with an electrical signal. And this type of wavelength division multiplexing allows you to extend your optical links not just with one channel, but with multiple channels, each carrying its own wavelength on the fiber. So, and for that you need what we call a wavelength multiplexer and demultiplexer. Now, this function of wavelength multiplexing and demultiplexing, it's essentially separating a broadband optical signal into many different wavelength bands. So you can see that multiplexing or demultiplexing system has a similar function as, for instance, a spectrometer, which you could use for sensing. Now, this allows you to scale your signal bandwidth to petabits per fiber, or petabit per second per fiber. And that's this kind of technique, this wavelength division multiplexing, is what today powers the internet. Now, optical communication is actually really good for this type of long-range communication, because these links allow you to very efficiently connect boxes together. And boxes started out being continents, like in the picture I just showed, but they're slowly decreasing in size. So we then find boxes that are the size of cities. And nowadays we're looking into data centers where people are connecting racks and shelves, and even within a rack, different blades together with optical fibers. So we're now down to the limit where boxes are in size on the order of 10 centimeter to 1 meter. Now, if we have these optical fibers and we have these photonic systems, If we want to build larger systems with it, we usually start off with building things like this on an optical table. But this is not necessarily very scalable, even if you use optical fibers. And you see in this case, all the yellow lines that you see in this picture are optical fibers, but still this is quite a convoluted system. And this brings me to the core of my talk. What if we integrate all this functionality on a chip? What can we manipulate the light on chips? Bringing information or bringing systems down to a chip has a lot of benefits. We've seen that in electronics. You can make much more complex circuits. Your performance goes up, your power consumption goes down. In the end, your cost goes down, and you can make these chips in very large volumes. Electronics has enabled an entire revolution of new systems just because you can embed an enormous complexity inside a very small, cheap package. Can we do the same thing for photonics? Well, if we want to do that, we need to be able to implement all the essential functions on the surface of a chip. So we're talking about the transport of light, filtering of wavelengths, a light source, like a laser, signal modulation and signal detection. And if you can do all that, if you can bring these together, you get circuits like we see here, for instance, like a very simple simple photonic integrated circuit where you combine a light source, a modulator, you filter the light, you finally send it to a photodetector, and you send it back and forth through optical fibers. Now, the key to making this work is that you treat this as a circuit. So the difference between treating things as a bulk element or as a system, where you model the entire thing as one geometric entity, towards a circuit where you treat things as building blocks that you connect together, is a very big difference. So if you want to scale up in complexity in photonics, you also need to treat your optical signals, your optical functions as a circuit, and then connect those functional elements, those building blocks, together with waveguides. So essentially the basic element of such a photonic integrated circuit is the waveguide. So you need on your chip, you need some way to define a strip of higher refractive index surrounded by lower refractive index that can confine the light, and you can guide it where you want it on the chip, just like you would put an optical fiber on a planar surface. But now you need to be able to manufacture a lot of these waveguides together on the same chip. Now, inside a waveguide, the light propagates essentially along the path of the waveguide, and we can abstract that light as a single guided mode. Basically, it's a blob of light which is centered around the core of the waveguide, but we also see that some of that light is actually extending slightly outside of that core. Still, the entire blob of light, the mode, is guided or is confined or is bound to the waveguide. And that mode propagates at a fixed velocity, so that the entire package of light moves at a fixed velocity through the waveguide. We can identify two types of velocities. We can identify a phase velocity, which is kind of the wave fronts or the phase fronts that propagate. But if you send a modulated package of light, like a bit on and off, or like some modulated signal, that will usually propagate at a slightly different velocity called the group velocity. So that's something to keep in mind if you design photonic chips, is that there is a difference between what we call the phase velocity and what we call the group velocity. And depending on the functionality, either one or the other is important. Now, if you want to build a circuit, you need more than just a waveguide. You need components like, for instance, a splitter, where you can split light in two parts. Or more commonly used than a splitter is a 2x2 coupler, where you also split light in two parts, but you basically, instead of just splitting one input port, you're mixing two input ports into two output ports. And this type of 2x2 coupler can be implemented in such a broad rectangular waveguide, which we call a multi-mode interferometer, or it can be implemented by coupling two waveguides close together, side by side, which we call a directional coupler. Now, with these building blocks, we can now start making more complicated circuits. For instance, we can start thinking about making wavelength filters that separate out wavelengths. Now, wavelength filters on a chip there's different ways to implement them, and there's different types of wavelength filtering functions that you might want, depending on your type of application. For instance, you could talk about what we call a channel drop filter, where you have a lot of wavelengths coming in, and you filter out one particular small band of wavelengths. But you can also build something like an interleaver, which filters out even and odd wavelength bands into the output channels. And then the last and often quite useful function is called a multiplexer, which in one operation separates all the wavelength channels in its own output waveguides. Now, these type of wavelength filter functions can be used for separating channels in optical communication, can be used for sensors, can be used for spectrometry. But all these filters are essentially built on the same operational principle. You basically split your light up in one or more paths, and then you delay that light along some of those paths. And then you bring everything together, and because light is a wave, you will now, depending on the path length difference, you will have some constructive and destructive interference at the output, which means that you will get some wavelengths going into one output and some wavelengths going into the other output. And the most simple version of such a wavelength filter is a Mach-Zehnder interferometer, which we see here, which splits light in two parts, and that with a certain delay delta L. And at the output, we see that the wavelength transmission in the outputs is a sinusoidal, which with a period that's inversely proportional to that path length difference. If you want to make it more complicated, you can just add more of these path lengths. A second type of wavelength filter, which also is based on the fact that you have certain delay, is called a resonator. And this is an example of what we call a ring resonator, where you have your light coming in, you have a coupling section where a part of the light is coupled to your ring, and then it starts circulating. Now, because light is a wave again, it will only work the circulation will only work if the wavelength of the light fits inside the ring an integer number of times, so that the waves nicely add up. Now, if that happens, for those wavelengths, your light is coupled out to the output, while for the other wavelengths, it basically cancels out and your light just passes through. So these type of ring resonators and Mach-Zehnder filters are essentially the basic building block for all types of spectrometry or wavelength division multiplexing applications. They can all be described as some combination of those devices. Another important element that you need in a photonic integrated circuit is some way to interface with a fiber. And as we will see further, that's not always easy because the waveguides on a chip are not necessarily, they don't necessarily have the same size as an optical fiber. So you need to squeeze the light from the fiber into the waveguide, and you need to be able to convert it back from the waveguide into the fiber. So you need some form of fiber coupling device. Now, all the devices that I showed you now that make up a photonic integrated circuits are what we call passive devices. These are devices that do not take any electrical signal to change their behavior. Essentially just manipulating light on its own. If you want to do more complicated things, you need active devices. Devices that use some electrical signal or make some interface between the electrical domain and the optical domain. For instance, the most straightforward device that we have there is what we call an electrical modulator or electro-optic modulator. It takes an electrical signal, it takes an unmodulated continuous wave beam of light, and at the output you get some modulation. You get a signal imprinted on that beam of light. And the technique to do that electrical modulation can be based on different physical mechanisms. It can be based on temperature, it can be based on the presence of electrical carriers and like electrons and holes. It can be based on intrinsic electro-optic effects of the material. And depending on the speed at which you operate these, this effect can be used for tuning, or can be used for switching, or for fast signal modulation. Also, it's important to remember that these modulators, there are a lot of different types of modulators. So some modulators modulate the amplitude or the intensity of the light. Some modulate the phase, for instance. Now, on the opposite side of the modulator, we need some way to translate our optical signal back into an electrical signal. And for that, we typically use something like a photodetector. So where you get modulated light in, and the incident photons are converted into an electrical current or a voltage. So in a photodiode, the absorbed photon creates an electron-hole pair, which can be collected by a readout circuit and amplified. Now, a last function that is very important in an optical circuit is a light source. In some way, you need to be able to get some light into your circuit or to have some light to process. And so the typical elements that you use there are either a light source, a laser, or an LED, or some amplifier which combined with your circuit can be turned into a laser. Now, to make these light sources, you need materials that are really good at emitting light. So there's a certain selection of what you can do with your photonic integrated circuits depending on the materials that you use. And that brings me to one of the key points in the landscape of photonic integrated circuits. Unlike in electronics, where 99.9% of the electronics is all made in silicon, in photonic integrated circuits we see a really wide variety of materials. For instance, if we want to make a laser or a light source, we almost always end up with 3-5 semiconductors, because these have a direct band gap that is really good at emitting light. While if we want to guide light, we want preferably a light with a material with low loss. And so we end up with glasses or polymers. 3-5 semiconductors work, but silicon works, but they're not as good and low loss as, for instance, glass and polymers. If you want to do fast signal modulation, you need a material that has a fast electro-optic effect. And then you end up with exotic materials like lithium niobate or some exotic polymers. But you can also look at 3-5 semiconductors, for instance. But silicon is like not a very good material for that. And then for detection, you have the same problem. You also need a material that can absorb light and efficiently convert it to photons, to electrons, sorry. So that means that if we look at the landscape of photonic integrated circuits, we have a table like this where you can set off all your different material systems and look at all the pros and cons, and you will find that they all have their strengths and weaknesses. And that's why if we look at the photonic integrated circuit market today, we see that it's still quite largely fragmented. We have a large section, actually the majority of the photonic integrated circuits today are still indium phosphide, so 3-5 semiconductor. But you're also, depending on the wavelength, you might prefer gallium arsenide. Now you also see that there's silicon, there's lithium niobate, there's silica on silicon. So there's a lot of different material systems that can be used. Now one that I want to focus a bit more on in particular is what we call silicon photonics. Because if you look at what's happening online and people talking about photonic integrated circuits, silicon photonics gets really the largest part of the attention. So what is so special about silicon photonics? It's really, according to many analysts, it's the one technology that's really pushing the growth of photonic integrated circuits nowadays. So why is that? There's no good reason actually. If you look at it on first sight, silicon is really a bad material for photonic integrated circuits. It has no indirect band gap, so making a laser source out of it is really not that easy. If you want to use it as a waveguide, okay, the material itself is quite low loss, but fabricating it in such a way that you don't get a lot of absorption or that you don't get a lot of losses is not that easy. There's no efficient modulation mechanism in silicon. And also, if you're using it for telecom wavelengths, silicon is transparent. So it has poor absorption for telecom wavelengths. So why would you want to use it? Still, you see that if you look around the world, there's a ton of companies that are really betting heavily on silicon photonics. And nowadays, again, with the driver of telecom and datacom, we see all these companies pushing silicon photonic solutions for really high-speed data center and metro transmitters. So what makes silicon photonics so unique that people are so enthusiastic about this? Well, if you can look at the definition of silicon photonics as this one. Silicon photonics allows you to do really high density integration of photonic integrated circuits. And now comes the catch. Using CMOS process technology in a CMOS fab. And that's the unique property of silicon photonics here, is that you can use these materials, you can process these materials in the same manufacturing infrastructure as CMOS electronics. So all the investments that have been made to build these multi-billion-dollar fabs to make electronics could be leveraged to make photonic integrated circuits. And as a result, by using all this state-of-the-art technology, you can integrate really a lot of complex functionality into small chips and potentially fabricate them at high volumes and low cost. Now, silicon photonics comes with a lot of flavors. I mean, if you just look at this definition, there's a lot of materials that really meet these requirements. For instance, we have the standard, what we call the standard submicron silicon photonics, which operates between a wavelength of like 1.2 and 3 or 2.5 microns, which is, I think, the most popular brand of silicon photonics because it fits squarely in the telecom wavelength range, which people like to use for optical communication. But if you want to move to shorter wavelengths, you can, for instance, start using materials like silicon nitride, which is transparent for much shorter wavelengths. The index contrast is not as high as in silicon, but it's quite good. If you want to go to longer wavelengths, you can start using germanium, which is since 15 years an accepted material inside a CMOS fab. So silicon photonics allows you to scale. It has this large-scale manufacturing capability, but at the same time, the use of materials with a high refractive index allows you to scale your waveguides down to sub-micrometer scale. To understand why this is, let's look at waveguides that are like kind of an optical fiber. You see, when you make a waveguide out of glass, like an optical fiber, which is surrounded by another type of glass with a slightly smaller refractive index, you get fairly large waveguide cores, on the order of 10 micrometer, in order to guide the light efficiently. Now, if you go to materials with a higher refractive index contrast, like for instance 3-5 semiconductors, where you can have an index contrast of 10%, you can scale your waveguides down to a scale of a few micron. If you go to silicon, you can get an index contrast of more than 200%. Your waveguide now can be scaled down and shrunk down to an area, a cross-section area of like half a micron by half a micron, or even less. So you end up with waveguides like this, with a high effective index core and a low effective index cladding, where your light is confined in a mode that is only 500 by 200 nanometer in size. And this is a really strong enabler. Not only does it make your circuit smaller, it allows you on the same footprint to make more complex circuitry. Just as an example, these are 3 circuits of an arrayed waveguide grating. It's a type of wavelength demultiplexer, but in 3 different technologies. And as we go from very low contrast, silica on silicon here, all the way to silicon on insulator over there, we see that we get like a factor of 10,000 reduction in footprint, which means that on the same chip area you can put 10,000 times the functionality. And that's what enabled electronics to become so successful. By shrinking down the transistors, you could get more complex functionality. The complexity did not come from the fact that the transistor was better. The complexity comes from the fact, and the functionality from the fact that you put so many transistors together on a chip. And so what we see now in silicon photonics is something emerging like a Moore's law for silicon photonics, where we see on the order of thousands and going to 10,000s of optical components on a chip, scaling up the complexity of the circuits. And so we've already seen published like really complex circuits where we have like these thousands of optical elements together on a chip, and a lot of these elements are also electrically controlled, so you can have kind of switching circuits. Now let's dive a little bit as an introduction on how these circuits are fabricated, what is needed to make a photonic circuits, and let's focus on first on how to make the waveguides themselves. So if you look at silicon photonics, it's usually based on a layer stack that looks a bit like this. You have a silicon substrate, which is the wafer, and then you have 2 or 3 microns of insulator layer. It's not an electrical insulation layer, or it doesn't act as an electrical insulation layer. It acts as a low index layer that separates the silicon substrate from the guiding layer in silicon at the top, which is on the order of 220 nanometers. Now, if you want to create patterns in these, you essentially start with coating a photosensitive resist. You imprint a pattern in the photosensitive resist. This can be done with an electron beam, or this can be done with an optical stepper. Then you develop that resist, and then you use an ion etching, a reactive ion etching, to etch away the silicon in the exposed areas. And in this case, for instance, you do a pattern of a grating, which is etched 70 nanometer deep. And then you can repeat this kind of steps again. You can deposit resist again. Now you pattern some other patterns. In this case, it would be trenches that define the waveguides. And then you etch these trenches away. And what you see now is a circuit that consists of 2 grating couplers to interface to a fiber and a ring resonator connected with waveguides. Now these passive functions essentially just require cross sections that look a bit like this. So with multiple edge levels, you can define optical waveguides, you can define gratings, etc. If you now want to introduce new functionality like active functions like modulators, you have a bit of a problem. In the end, you just have silicon there. It has no electro-optic effects, it has no photo detection for telecom wavelengths, and it has no optical gain. So how do you add these active functions to this cross-section? Well, for the modulation, people in silicon photonics came up with a clever trick that bypassed the problem of silicon as a not really good electro-optic material. They basically used the presence of carriers in silicon. And the presence of electrons and holes affects the optical behavior. So what they did is, using all the tricks they know, they were already developed for electrical engineering, is to make PN junctions, like diodes, inside your waveguide. And by applying a voltage over that diode, you can pull out the carriers or you can inject carriers there, which modulates the refractive index. Note that that also modulates the loss, because these carriers can be can introduce quite some optical losses. So that allows you to do electrical signal modulation, and you can do that in different geometries. You can do that in the left one. You can do that by using a traveling wave electrode and a Mach Zehnder interferometer. So you embed this modulator inside an interferometer, or you modulate it in a ring resonator, which we see on the right, where you put your diode inside a resonant structure, and then you change the wavelength, the resonant frequency of the wavelength. And we see that that works pretty nicely. Now, if you want to do modulation, you can use these carriers. If you want to do detection, you also have to come up with some new trick. And there, the trick is to do epitaxially grown germanium into your silicon photonics. So you basically grow a germanium layer on your silicon photonics. The germanium has a much smaller band gap in energy, which means it absorbs these telecom wavelengths very nicely. But of course, you need to go through a process where you have a very high quality epitaxial growth of germanium, which is not that trivial. So it took some time to develop this kind of processes. As a result, you see something like this, cross sections like this, where you see that you have a germanium which is properly contacted with the metals. Now that's photo detection. The biggest challenge in silicon photonics is its lack of a light source. And there's no really good trick to pull in a CMOS fab to make silicon emit light, especially at telecom wavelengths. So in the end, the approach is now to try and bring 3-5 materials to your silicon to make a laser. And the first approach that's still quite popular, and that's also part of commercial products, for instance, at Intel, is to basically just glue or bond 3-5 layers on top of your silicon photonics and then process a laser in it. That works quite well, but it's a quite convoluted process. The holy grail where people are moving towards at the moment is to epitaxially grow the 3-5 semiconductor in your silicon photonics. Just like they epitaxially grow the germanium, now grow 3-5 semiconductors. That's far from trivial, and there's already a massive amount of research invested in this, but we're going towards in the right direction with already first demonstrations of lasers in the silicon photonic platform, epitaxially grown. Now, imec silicon photonics platform embodies most of these functionalities. At this point, all of those except for the laser. So if you look at how that platform looks in cross-section, and this is a schematic cross-section of imec's platform, but it's also quite representative of what you see with other technology platforms in silicon photonics. So you see that you have your optical waveguide, you have high efficiency grating couplers, you have high speed modulators, and you have detectors. And then everything is electrically connected with 2 or more layers of metal in the same way as you interconnect optical electrical elements in an electronics chip. Now, on top of that, you also have integrated heaters. These heaters are not really used for fast modulation, but they are used to tune your optical behavior of your waveguides. So you can, for instance, implement a phase shifter by putting a heater on top of it. And because all these materials are temperature sensitive, the optical index, the effective index of the waveguide will change. You can also embed a heater, for instance, next to the waveguide. Now, heaters have the advantage of the fact that they're really easy to make. I mean, you just need an electrical resistor somewhere close to your waveguide. The big disadvantage of heaters is that they are hot. They burn power continuously. And we're talking about, depending on the type of material, we're talking about 20 to 200 milliwatts of power for just driving your heater. And if you need a lot of those, that's not going to work very well. So people have been looking at alternative mechanisms to implement these phase shifters. And already we have been showing carriers. They work quite well, but it's a much weaker effect, and it also introduces loss. But for instance, introducing other materials like liquid crystals, or even introducing moving elements like MEMS can bring a solution. Now, all of these type of integrations require, again, some careful thinking, because you have this cross-section of this platform. You now need to introduce liquid crystals, which is not that trivial. So you need to etch a hole in your device, where you can then deposit your liquid crystal. Now, once you have done that, if you can do that, that works a treat. I mean, you can really get very high efficiency phase shifters and actuators in your photonics. This is an example of where we embedded a drop of liquid crystal inside our silicon photonic circuit. And everything else in the circuit still works. You can do a similar approach with MEMS, for instance, trying to make movable elements in your silicon photonics. Not that trivial, because you now have to undercut your waveguides. But again, if you are careful in developing your processes, you can get really nice results where you have these freestanding waveguides, which you can then modulate. And what you see here at the bottom is a phase shifter that modulates the phase of the light. And this is part of a European project called Morphic, which we do together with EPFL and KTH, amongst others, to design these high-performance MEMS devices inside an existing silicon photonics technology. And again, that works quite nicely. You get very high efficiency phase shifters. Now, if you have all these elements together and bring them together in a circuit, like this, for instance, this really becomes more complex. So if you want to design this, you don't have to design just the geometry of the circuit. You have to abstract the circuit down to building blocks which you can connect together. So very much like you design electronic circuits. And that means that on the design side, you also need certain functionality. You need a way or a mechanism that abstracts all the geometric and process knowledge that is being used by the fab and hand that over to the designer. And in electronics, this is called a PDK, or Process Design Kit, or Physical Design Kit. For photonics, these PDKs are slowly emerging or slowly coming to maturity. PDKs for photonics have been around now for like 10-15 years, but they were fairly rudimentary. Nowadays, we see more and more complexity being embedded into these PDKs. And that allows you to more and more adopt the same design methodology that is used for for electronic integrated circuits. So building on the experience of electronic design automation tool to get first time right designs for photonics, we're not yet there, but we're moving slowly in that direction. Because in the end, the whole idea of such a design flow is to translate the idea into a working chip. So you start by making an abstract description of your circuit, and then gradually you implement it as an actual geometry that can be fabricated. Now, just an example of how such a circuit design works. Well, let's say that we build an optical transceiver. Well, we need to design it, fabricate, package, and test it before we know it's actually gonna work. So you take these building blocks like modulators, grating couplers, etc., and you integrate them together, like for instance in 4 channels of 25 gigahertz with a modulator, and then 4 receivers that couple to a photodetector. But now if you want to change or upgrade your link, you can use these same building blocks to design another type of circuit, like for instance a coherent transceiver. Or you can, which has an IQ modulator and a 90-degree hybrid at the receiver side. But if you want to use it, for instance, in yet another type of modulation scheme, for instance, wavelength division multiplexing, you can again take the same type of building blocks, it's just reorganizing your circuit. So now you have 4 modulators that each carry their own wavelength. You multiplex them together in a wavelength multiplexer, and then at the return signal is again demultiplexed and sent to 4 different photodiodes. Now the key thing is that such an iteration cycle, every time you want to build a new circuit, it takes you like 9 months to a year to get it done. And it also costs a lot of money. So your feedback cycle in your design is 9 months. If you have a good predictive design process, you should be able to do that in hours, days, or weeks. At this point, photonic integrated circuit design is not yet at the point where you can do it. So it's a kind of costly proposition. You need something that allows you to predict in advance what is going to happen after you have fabricated your circuit. The difficulty in this kind of predictive capability is variability. These silicon waveguides that I showed before, they are only like a few hundred nanometers across, but they're so sensitive to even nanometer scale variations. The high index contrast means that if you remove a cubic nanometer of material, you will already be able to observe it. That means that you need really, really good process technology, and even then, you will be suffering. Just as an example, if you change your width of your waveguide with 1 nanometer, your filter response will shift with 1 nanometer, which is already a few communication channels in a telecom network. And then if you look at actual variations on a wafer, this is a wafer of a couple years ago, you see that we can, within a wafer, see 16 nanometer of line width variations. So that's an enormous number of, that's an enormous shift. So how do we cope with such variability? Well, there's 3 ways to do that. First of all, you can keep on improving your fabrication technology and design your building blocks so that they're as tolerant as possible. The second technique is coming up with a circuit design methodology that allows you to predict how this variability will affect your circuit and then allows you to optimize your circuit for lower variability. The last technique to do that, to address variability, is to go towards more tunability and even programmable circuits, where you can reconfigure or retune your circuit for a certain functionality after the fact. So, if you want to cope with variability, first of all, improve fabrication. This is something that's continuously ongoing. So you can go to better fabrication tools, which typically means moving from 200 millimeter to 300 millimeter wafer fabrication, which has better lithography, better etching techniques. You get higher quality substrates with better uniformity of your layer thicknesses, and you really introduce very stringent statistical process control. Now, the second technique is going towards more variability aware design. And that's not that easy, because you need very accurate models of your devices, but you also need to know how they are being affected by different effects that happen during fabrications, like how sensitive are my components to line width variations and thickness variations. And you need to know how these quantities are usually distributed over the wafer. So what's a typical distribution pattern of thickness variation or line width variation? You can combine all that together using Monte Carlo techniques or stochastic techniques to get some form of yield prediction. But this is still in a very rudimentary stage in photonics. So the last part, or the last technique to cope with variability, is tuning. So you can actually start compensating and improving and optimizing all the elements in a photonic circuit dynamically. So instead of building a circuit like this, where essentially all the elements are fixed, you can now, for instance, replace the filter, which is the most sensitive part, with a tunable filter, where all the elements are tunable. And that opens up an whole avenue to making circuits that can actually be reconfigured or slightly modified to do multiple functions. And what we're seeing today now is circuits like this, where you have, this is called a multipath interferometer, where you have circuits which can be reconfigured to do different types of operations, or, and this is one step further, or can be really like operate as a multifunctional processor that can process not just electrical, but not just optical data, but also electrical data. And such a circuit, just as an example, you can, by having all these tunable elements, you can route your light wherever you like. And this is the kind of programmable photonic circuits that most of my research is now focusing on. You can do multiple routes of light. You can even route light through both the same coupler and introduce crossings. And then it becomes interesting, because these couplers are not really switches. Everything is analog on such a circuit. So you can do partial splitting, and you can combine it again to form an interferometer, which can then be used to make a programmable wavelength filter. You can even introduce resonances in such a circuit that allows you to make really very sharp notch filters. And so the first demonstration of such a circuit was done by the University Polytechnic of Valencia, by the group of Jose Capmani. And they actually introduced this concept of a general purpose photonic processor, which could not just have optical signals going in and out, but also process high-speed electrical signals by modulating a high-speed electrical radio frequency signal or microwave signal onto an optical carrier, and then process it in this optical mesh of waveguides in the middle. Now, inside of this mesh is an electrically tunable waveguide mesh. So, and this is key, it's electrically tunable. So it becomes essentially programmable. The challenge here is that you need to interface all these electrical couplers and phase shifters with a driver and a controller, and then you need to read out what their status is, which means you need very tight integration of photonics and electronics. And this is one of the key challenges for silicon photonics today, is really good integration of photonics and electronics. And you can do that by trying to integrate the silicon photonics and electronics on the same chip, which we see in the top right corner. But a more common approach is using flip chipping or 3D stacking, or even just wire bonding here. Now, you'll hear more about these packaging techniques, I guess, in the next presentation. So if you want to build a photonic circuit or a programmable photonic circuit, you don't just need the photonic chip. You need to bring everything together, fiber interfaces, microwave interfaces, driver electronics. Everything needs to be properly packaged. And then you need, on top of that, you need software layers to make everything work. So the complete technology stack for photonic integrated circuits and programmable photonic integrated circuits is not just a photonic chip. The photonic chip is just the bottom layer. You need everything else on top of that to make everything work. Now, if you have a photonic chip or a general programmable processor, you can use these in many different applications. So just as some examples where you could use photonic chips or photonic processors, optical communications is an obvious one. That's been the mainstay driver for photonic circuits since decades. But you can now see them being deployed in a much wider scale in buildings for fiber to the home, but also for converting legacy RF signals like ADSL signals to optical signals. And one of the key drivers for this type of architecture is also the need for 5G antennas to be very widely distributed. So you need lots of these antennas, and these are going to be optically connected to the central office. Apart from communication, you can also see a lot of sensor systems which will make use of these optical chips. Like for instance, fiber sensors are already being used in constructions for buildings and bridges and airplanes. But you need efficient readout circuits for these fiber sensors. So if you want to make a really widespread use of optical fiber systems, sensors, you need these photonic integrated circuits. Also in cars, you can use these photonic integrated circuits to do multiple sensor readouts and even go as far as using them as an engine for a LiDAR for self-driving cars or a microwave engine for lightweight drone radars. And these sensors can be extended to the biomedical community as well. So you have biosensors, optical biosensors that can do specific molecular analysis, or I think this is useful to this audience, you have also optical coherence tomography, which can be very useful in dentistry, but also in ophthalmology. And then finally, some other applications you can find, for instance, security, quantum communication, for instance, or optical hashing, or like doing Bitcoin-like of calculations, blockchain calculations in optics could be extremely useful. So that brings me to the end of my presentation. So overall, photonic integrated circuits have a lot of benefits just by bringing everything to the chip. Similar benefits as you find in electronics. So better performance, lower size, weight, and power. One of the key technologies driving this is silicon photonics in all its flavors, which also includes silicon nitride waveguides, germanium waveguides, etc. And that's actually driving the fact to more complex circuitry, which is slowly creating the kind of scaling that we see in electronics, where the functionality is no longer determined by the individual building blocks, but by the complexity of the circuit. And programmable photonics is one exponent of that evolution. So with that, I thank you and feel free to ask questions.